Up next, we move to our spotlight presentation series, and first we have Rounak Bardia from Shell. Please join me in welcoming Rounak.
Thank you. Thank you for the organizers to provide us with this opportunity to present. And my name is Rounak Bardia. I am a computational science researcher from Shell. We are part of the research and innovation arm of Shell. And it has been a packed past 2 days. I've seen a lot of presentations talking about different successes that different companies are seeing in their AI and foundational model journey. This particular presentation might look a bit different. It is of course very topical, but also shows a little bit of a limitation of what we are seeing in our experience with integrating AI workflows within scientific work. So the primary thing that we tried to do in this project was to create like an evaluation framework. We have to identify what Shell would require for integrating AI into its workflows. We're not going to build foundational models. I think there are other companies that are doing it far better than us. What we will be doing is things that will be generating from these foundational models, how they can integrate with our workflows, and can we actually quantify whether they are good or bad. This is just a cautionary note. There's nothing in this presentation that you should take any marketing advice with or any kind of shareholder advice. Before I present my work, I want to introduce what our group is. It's a large group based out of all the three hubs, research hubs of Shell: Bangalore, Amsterdam, and Houston. A big part of it sits out of Bangalore. We are a team of physicists, chemists, chemical engineers, mechanical engineers, and electrical engineers. The primary focus of this group is to solve all types of really complex, real-world upstream oil and gas, new energies, and downstream chemical problems through computational methods. So we have basically different kinds of methods that we deploy, and based on that, we have these different teams. So we are essentially using all of these computational methods like molecular dynamics, Lattice-Boltzmann approach, finite volume methods, the whole gamut of things, which have developed over the last 4 decades, as some of you might be aware, how these complex numerical methods have evolved and how we are able to solve some of these complex problems. But that also has added more complexity in just using these tools, in just using these methods. And that's where we as a group see the use of these generative AI tools to reduce this complexity or make it more easily accessible to all the domain-aware physicists and chemists. We can use generative AI, use natural language to basically deploy these tools for us and not have those niche computational know-how and leave that for the expert problems. We've seen an uptake in literature around that. You can see at the nanometer scale from molecular dynamics, there's attempts at automating agents that can basically use a natural language query and run a Palabos simulation or another molecular dynamics simulation. A lot of continuum work related to OpenFOAM agents. OpenFOAM is the primary library that we have used for our work. And also at the level of process modeling using Unisim or Aspen through these natural language queries and trying to automate some of the workflows. So across all of these scales, our team operates. And across all of these scales, we're seeing the use of generative AI and use of agent layer on top of that generative AI to create these simulations and execute these simulations. But while these papers, and these are mostly archive papers at the moment, you can see that most of these papers have come up in just this last year, 2025. So there's been a massive boom in these AI agents in this past year. And there's a lot of good claims around it, but there's an important caveat there that there is not a lot of rigorous analysis of what these AI agents have been able to achieve through these generative AI layers. So that's what we wanted to assess. Do they all perform as expected? There has, of course, been some evaluations that have been done for these agents. But as you can imagine, being the users of these methods, there are a lot of experts sitting within the community working inside Shell and, of course, outside. What are the kind of evaluations we should be doing is something that we need to ask very critically. In most of these papers, they're very simple evaluations of, let's say, when they tried to set up a particular simulation case, it worked or it did not work. That's a simple binary yes or no evaluation. But then there is a little better evaluation of people trying to use the evaluations used for LLMs, actual string level evaluations, and seeing whether the strings that are being generated are correct or not. That's one layer of evaluation, but it doesn't make it very domain aware. It doesn't make it aware of what a Palabo simulation in molecular dynamics or what an open form simulation is supposed to be. So in that respect, we basically chose one particular type of solver and one particular type of agent to create an evaluation framework. We saw that there was insufficient focus on domain-aware analysis, and so that's what we tried to do. We picked up OpenFOAM. It's an open source library of a lot of finite volume solvers, and it is used primarily for fluid flow simulations, heat transfer simulations, and such. This is used internally in Shell, but also globally. There's been a growth in over the past decades. There's a very active community around it. And hence, we see a lot of AI agents that have already been generated for OpenFOAM to automate the generation of OpenFOAM simulations. So before I get into the evaluations aspect of it or the agent aspect of it, what does an OpenFOAM simulation look like? I know there's a very diverse audience here. So just to give a flavor of it, when you are trying to solve kind of a flow simulation or a large domain simulation, you have to create the domain for the system. You have to discretize it. So essentially, that's called meshing. You discretize the simulation. You initialize it. So you set up the fields, how the initial domain looks like. And then you try to solve the problem through the back-end numerical methods that have been implemented to solve your PDEs. In OpenFOAM, this is primarily achieved through a whole host of text files. There are a lot of files which are to be developed in a very standardized format. And there's just an example format that is shown here, just one of those files. But for a typical simulation, you're developing anywhere like 8 to 10 very standardized files following a specific set of keywords. So the agent that we develop for automating these OpenFOAM workflows would have to follow these standards, would have to follow these keyword assignments. This was one of the agents that we picked up off the shelf from some of the developers who have built this agent at RPI in New York. This is like a typical architecture that you would see in most of these simulation execution agents. You have a user query going in, and then you have an architect agent. What that architect agent does is it has a set of RAG database. So for folks who are unfamiliar with RAG, it's essentially an indexed set of documents that have been pre-processed and kept as a repository for the agent to access when there is a query. And when there's a query, I try to find out the most similar indexed document. That's your RAG workflow. So here most of these agents, and we are talking about this particular agent right now, they use OpenFOAM tutorials. So there's a whole gamut of tutorials that have been developed over the years for OpenFOAM. It accesses all of the different types of physics solvers that OpenFOAM has. And those tutorials are used as the indexed documentation within their RAG database. This is what a query basically tries to get. What is the most similar tutorial within OpenFOAM that I can reference and generate my files from? Once the architect agent identifies that tutorial, you have another agent that generates the input files. It's deployed like that. And then it tries to execute the set of files that it has generated. Once if it sees an error, it tries to review it and fix the input files. And there are about a few iterations you would do before you either call it a success or a failure. If it is a success, you end up with something like this, where you have a whole folder of the simulation case, and within a folder there are like several subfolders. Each of those subfolders have a set of text files. As I said, in OpenFOAM you have like a whole host of text files that you are generating to actually execute the simulation. So now, so far, hopefully I've set up like the platform as to what we are trying to do. And this is now the meat of the work. So we wanted to develop our evaluation methodology. And what we want to do here is we want to generate manually some of these test cases. We'll generate these test cases and then ask the agent a very engineered query whether it is able to generate a very similar test case. That's the essential setup how we are running our experiments. And to basically compare these two out, compare with the ground truth, you are basically converting everything into like a keyword sort of dictionary that looks like a JSON file, just like. within the framework that we have built together, we created two different modalities. One is, as I mentioned, a domain-aware rules-based modality, where we use some of these string-based metrics that are often used with LLMs, but also domain-based open-form dictionaries that the evaluation agent basically tries to interface with and tries to understand whether the agent has actually followed open-form set of guidelines or not. So in terms of the string-based comparisons, we have sort of a lexical similarity with two of the scores that are typically used, Levenstein distance and Rouge scores. OpenForm also follows a very nested dictionary kind of format. So wanted to build like a structural similarity part as well. So we have a tree edit distance that tries to see whether the tree of the nested dictionary looks similar between the ground truth and the actual agent output. And then the semantic similarity, where you are trying to assess whether the agent has actually used open-form keywords. Let me give you an example. So if you are running some kind of a compressible flow system and the open-form solver name is actually something like Sonic Foam, but because it's an LLM that's working at the back end, it may just call it compressible foam. It may not call it Sonic Foam. Those kind of errors may occur. And we have seen some of those errors that, that lead to failures in our solvers. So that's the domain-specific keyword that we should be following. And we should be able to identify that this is where the solver failed. So that's the semantic similarity aspect. There are a whole host of dictionaries. I'll just flash that in a bit. But to combine these rules-based scores, we wanted to create a weighted score and to give more weightage to the domain-aware aspect of it. And that's how we have built it together. So the intent is not to get whether the agent works or not. That's a fairly easy binary yes or no. The intent is to identify whether we are penalizing small errors more or whether we are basically trying to understand how far has the agent achieved the goal it was set to do. And as I mentioned, in terms of the semantic assessment, we created manually these open-form dictionaries of keywords that each keyword should follow corresponding to the other keywords. There are more dictionaries. I'm just showing you a sample of 3. Depending on like boundary conditions, numerical schemes, turbulence models, what are the specific keywords that these should be using and whether the actual agent is following it. In fact, if the ground truth uses a particular model, but the agent uses a different model, however, it is from the same list, it is not penalized that significantly. That's a very key difference that you bring in terms of the domain awareness. I talked about the rules-based, very prescriptive form of evaluation. There is another set of evaluation which we try to do the other modality. I think the speaker yesterday, Tosh from Meta, talked about LLM as a judge. And that's a very common modality that now is being used. We created 2 judge experts. One that basically assesses the agent output in terms of its correctness with physics that the query has asked. And then the other that talks about the syntax correctness. For each of the judge, we basically created like a rubric of how it should rate the output of the agent. And basically, this is the kind of rubric we followed, very simplistic rubric. As I said, we're just trying it out. We're engineering our way through it and trying to understand what are the things that we can play around with. And does it give us some indication? Again, to combine the 2 judges, we created like a weighted score. It is a very from the looks of it, how we have engineered the prompt and how LLM as a judge is typically operating, it is a very comprehensive approach. You give all of the agent output, compare it with all of the ground truth and see how, and just ask the LLM how did it perform. It seems very comprehensive, but as LLMs, this is a very stochastic approach. Even this judge itself will have some stochasticity in terms of how it is scoring the output. The stochasticity seemed to be small, but it was there. So far, I've talked about the evaluation methodology. I've talked about the kind of agent we are trying to evaluate. I'll briefly talk about our design of experiment, how we wanted to analyze different simulation cases. We didn't want to go completely haywire. Although in reality, in Shell, we are never dealing with simple test cases. We're dealing with very, very complex multi-physics systems. You're dealing with turbulence, reactions, thermal modeling, flow, complex geometries, and all of that. But we didn't want to throw the tractor at the agent first. We wanted to see from within its tutorial database. It has its own RAG database. We just picked some of those tutorials. We said, we're not going to tell that this is the particular case we wanted to solve. We'll give the description of those cases, and we'll see whether it is able to understand and actually recreate that case. So we just picked up 12 cases, and we gave each case, we created like 3 levels of prompts. At an elementary prompt, you just give like a simple conversational prompt. At an intermediate level, you are giving more of a labeled prompt. You give 5 keywords that are typically given by fluid flow analysis users. And then an expert prompt, which gives a lot more extensive information. So we expected some variation within these. In the interest of time, I'll jump to some of the results very quickly. But essentially, we ended up running over 300 experiments. How it became 300 is basically we ran each prompt 5 times. Because again, there's a stochasticity of LLM. We wanted to see if it is successful all 5 times, fails all 5 times, and in a more convoluted way, it may succeed sometimes and fail other times. That's a little more complicated place we don't want to be in. This is just an example of these kind of prompts, a very conversational paragraph type of prompt that we gave as a beginner elementary prompt, an intermediate prompt where we give it point-wise information, and an expert prompt where we give it a little more detailed and several more keywords. Now I'm going to jump into the results part of it. For the agent, we executed it with the O4 mini LLM, and we see the agent basically fails in a lot of these simulations. So it is not able to do an end-to-end setup and execution and correct execution at that for the simulation. So we basically are plotting on the x-axis 5 different categories. Where did the agent fail? Did it fail at the meshing stage? Did it fail at the initialization? Whether the solver failed, or whether the solver executed but did not regenerate the correct results. And finally, the 5th one is basically where everything worked perfectly. Of course, as we said, the intent was to evaluate whether the agent was able to perform a reasonable good job. So higher scores are basically it is able to create most of the files, but it may be failing at one of these points. This is the first one was the rules-based evaluation. The second one is more of the LLM as a judge. And you can see the clustering of LLM as a judge evaluation scores in the middle. It doesn't really give us a lot of spread. It doesn't give us a lot of information about where the agents fail. But the key headline here is that only 38% cases succeeded. This is from the tutorials. We just gave a descriptive analysis, explanation of those tutorials. It didn't perform very well. The papers had basically put together for GPT-4o their results. And we should say that even for GPT-4o, the performance was even worse. Although they claimed there was about 80% cases success, we didn't see that. We saw about 15% cases succeeded. A lot of the cases failed. And the more difficult part is that about 13% cases showed that the solver executed, but the results were incorrect. And this is something folks who are using LLMs on a very daily basis would recognize as a much more bigger problem. When you are depending on a solver to create your code and it starts giving you the wrong syntax or the wrong keyword, it's much more difficult to identify. It will create the whole code and you'll try to figure out where it created an error. If it throws an error, you know where the error is. But if it just runs the simulation, for an uninitiated user, they may just accept the result. For an initiated user, they will be confused as to where the problem is. So this is my last slide. We really felt after this exercise, we are a bunch of applied researchers. Our KPIs are driven by solving physics and chemistry problems. So we don't come from the computational science background. We're going to be using these AI tools. From that perspective, there's going to be a lot of uphill battle in terms of making managers and making lines actually accept some of these tools. There's got to be a lot of evaluations. This is not ready for prime time. Even if we improve the AI agent architecture, we will have only expert users still dealing with it. We can't really have regular users who don't have experience with computational work on this. Domain-aware evaluations did show a lot of spread in the scores, gave us a lot more insight. And finally, I think there is definitely a scope for improved evaluations. This was just one of our attempts at evaluating and one of the attempts that we showed here. I think there is a lot more gap in terms of domain-aware evaluations that we can build together. That's it. Thank you.
Thank you, Rounak. We can have 2 quick questions.
Yeah, hello. I'm Prashant. So like you were discussing about the CFD. So in CFD, we go through three major steps: the pre-processing, solver, and then post-processing. So like I can see like you are training a proper test cases. Instead of that, can you train in case of OpenFOAM? Can you train pre-processing in the case of mesh generation? Like either you can have a block mesh or other kind of meshing, and train that much data and check like if that is working, then you can go to the another step, that is the writing the initial condition and the boundary condition and setting the solver. That could be the another step of training, and then you can have the post processing instead of training everything as a test case. So that could be a better step of training a LLM model for creating a test case rather than directly training a test case at a time.
I agree from the first point of that we can break down the entire step into separate steps and try to create agents for each step. Firstly, we are not training. We are not doing any fine tuning or training here. We are using a RAG-based workflow. So we are using LLM out of the box and actually creating a documented database, and then it's retrieving that database based on similarity. We have tried the meshing agent. We have already built an agent ourselves. That is still very rudimentary. And more important for everyone to understand is the kind of geometries and meshes that a real world system sees. It is, firstly, we have very few of those. So in terms if you're thinking of training, there's not enough data. There are going to be very few of those. And it's very bespoke. A particular reactor will look only in a particular way for one or two cases. There's not going to be 1,000 same iterations. So it's not like a cat or dog picture. So there is merit to it. We are thinking more of an toolbox where it creates different tools of meshing and tries to leverage them together. Some sort of an MCP toolbox around it. But it's a great. It's where I think the next step is headed.
Hi, Shrivan. Thanks for the talk and the nice presentation. Myself, Himanshu Mittal from IIT Kanpur. So, like I have a question related to the prompts which you were using in this architecture. Since like you have distinguished prompts into three types, like the beginner and the intermediate and the expert. So how are you distinguishing them based on just the more amount of data being input in the prompt itself or the structure as well? And also how are you handling the hallucinations after that? If we structure the prompt much more effectively then after that, or just simple prompt is also giving hallucinations?
Okay.
Thank you.
So we're doing both. With each higher level of prompt, there is a little more information, but we did focus primarily on structuring the prompt. So the bigger focus was on structuring the prompt. And I must say, because we were doing large set of experiments, about 36 prompts here, if we type it manually, there's a lot of stochasticity. Like I and my colleague will type it differently. So we did basically use GPT-5 for creating these prompts. And then we made our own manual edits to wherever we needed it to be done. So that's how we did it. So that's first. And I think your second question was about hallucinations. Our intent here was to just test the agent as is, not fix its output. So if it was hallucinating, in some cases, as I said, it was creating like words, sentences inside an OpenFOAM case dictionary, which was wrong. If it was hallucinating, we let it be and it basically failed. And it was shown in a smaller scores. So that's how we were evaluating. We were focused primarily on evaluation or not making the agent work.
Okay. Thank you. We can catch up for more discussions during the coffee break. Thank you, Rounak.